In part 3 of the Unit 5 notes, we will be looking into creating the periodic table and periodic law. In 1869, Russian chemist and teacher Dmitry Mendeleev was writing a textbook for his students, and he wanted to organize all of the elements according to chemical properties. He arranged the elements in order of increasing atomic number into columns with similar properties. The result was the first periodic table of elements. His table became widely accepted because by noting trends in properties of known elements, he was able to predict the existence and properties of undiscovered elements, including scandium, gallium, and germanium, that were later found. Why do you think there are question marks where some symbols should be? So here on Mendeleev's periodic table, we can see where there is a question mark at a mass of 45, a mass of 68, and a mass of 70. These were gaps on Mendeleev's periodic table, but based on the properties of elements surrounding those gaps, Mendeleev was able to predict that eventually an element would be found with that mass. So Mendeleev was predicting the existence of elements. The pattern formed when comparing atomic mass to chemical properties works for most elements, but iodine and tellurium are an exception. Mendeleev placed those two elements in the correct spot on his table based on the properties while ignoring the mass, but he cannot explain why they did not follow the pattern that every other element seemed to follow. In the picture down here, you can see the switching of iodine and tellurium. So going down this column, we have the mass consistently increasing until we get to those two elements, where it goes to 128 and then back down to 127. What did Antoine Lavoisier, Johann Dobereiner, John Newland, and Dmitry Mendeleev all have in common? They were all scientists, and they tried to organize the element. When Dmitry Mendeleev created his periodic table, nobody knew about the existence of the nucleus. 2 years after the gold foil experiment, English physicist Henry Moseley examined the X-ray spectra of a number of chemical elements and found a relationship between wavelength and atomic number. His results led to the definition of the atomic number as the number of protons contained in the nucleus of each atom. He then realized that the elements of the periodic table should be arranged in order of increasing atomic number rather than increasing atomic mass. This explains why iodine and tellurium would have been in the wrong place on Mendeleev's table. The fact that the properties were somewhat connected to the mass was coincidence. Properties are actually much more closely related to atomic number. Periodic law states that there is a periodic repetition of chemical and physical properties of the elements when they are arranged by increasing atomic number. Here we are going to be drawing a Bohr model for lithium, sodium, and potassium. For lithium, our nucleus is going to contain 3 protons and 4 neutrons. Since this is a neutral atom, we can assume that there are going to be 3 electrons. So 2 in the first shell, and then 1 in the second. The atomic number for sodium is 11. It would have 12 neutrons, and since this is also neutral, we would have 11 electrons. So 2 in the first shell, 8 in the second, and then 1 in the final shell. For our last element, potassium, our protons would be 19 based on the atomic number, and our neutrons would be 20. For electrons, we would have 2 in the first shell, 8 in the second, 8 in the third, and 1 in the final shell. Based on the Bohr model for each, why do you think they have similar properties? Now, while these are all in the same family, the Bohr models all do look different. The one similarity that you should be able to see is that they all have the same number of electrons within the final shell of the Bohr model. These electrons are going to be responsible for the type of bonding that each of these elements can use. So each of these elements has the same number of electrons in the final shell. Valence electrons are the electrons in the highest occupied energy level or shell of an atom. These electrons can participate in bonding. Elements in the same group or family will have the same number of valence electrons, just like on the checkpoint slide on the previous slide. So we had one valence electron for each of the elements in group 1. Inner shell electrons are in the lower energy levels and they are not involved in bonding. In general, s and p orbital electrons at the highest energy will be valence electrons. For transition metals, this is more complicated because sometimes the d electrons will participate as well. In our picture that we have right here, you can see that each family will have a different number of valence electrons. So group 1 has 1, group 2 has 2, and then we have 3, 4, 5, 6, 7. When we get to the noble gases, helium will only have 2 because it only has 2 electrons. But all of the other noble gases will have a total of 8. In this image right here, you can see how the bonding might occur between sodium and chlorine. Sodium had 1 electron in its last shell, but it gives that electron away to chlorine, which only had 7. Now it can fill in that shell with the extra electron that it takes on from sodium. That concludes Unit 5 Notes Video Part 3. When we come back in Part 4, we will be looking into the atomic radius and the ionic radius.